on that. All right, guys, so here we go. Thermochemistry. You can actually get a degree in this. Yeah, it's interesting. One of the things that you're going to run into in this unit is what's called calorimetry. It's the study of energies of reactions. In lab, we'll actually build calorimeters, and we'll actually do 2 labs where we're working with calorimeters. But it's interesting, the professor at BYU that runs the freshman chemistry labs, he's actually a calorimetric, something like that. He's a chemist that does calorimetry. That's it. That's all he does every day as a research scientist, is he does calorimetry, and he figures out energies of reactions. Sounds horrible to me, but he loves it. So guys, here we go. And he's retired now. I don't know who took his place. So guys, when we think about thermochemistry, we understand that thermo, of course, means heat, right? You're going to find out today that it's actually, or not today, but in the coming days, it's not just heat, it's actually energy in general. And then, of course, we've got the chemistry piece. So guys, when we talk about thermochemistry, and feel free to write down any of this that you think is necessary. Guys, thermochemistry is the study of the energy changes that affect chemical reactions. For now, you can think of energy as simply being heat. You're going to find out later that there is another type of energy, which is the energy of disorder, and we'll talk more about that when we get into chapter 19. But guys, in either case, we've got to define the term energy. Now, guys, all right, we'll try it. Last year in general chemistry, we actually defined the word energy. Any of you remember what we said the definition of energy was? You don't need to look, but do you remember? Let me just tell you. Guys, last year in chemistry, and just don't write this down, please, but make sense of this in your head. Last year we said the definition of energy is the ability to make a change. Do you remember that? It was actually in September of last year, and we said that there's 2 kinds of changes. What are they? Physical and chemical. Remember that? And remember, we went in and we did the lab, and we dissolved things, and we precipitated things, and we burned popsicle sticks. And we said that there are physical changes and there are chemical changes, but energy is the ability to make a change. That is not actually the definition of energy. So what is the definition of energy? Well, guys, to figure out the definition of energy, we've got to take this one step backwards. So, is it true that energy is the ability to make a change? You bet. But that's not the definition, and here's why. If we take one step back, now we need to ask this question. What do you have to do to change something? That's half of it. One of it is work. The other is change the heat. So, guys, that is actually the definition of energy. Energy is the ability to do work or transfer heat. But guys, when we do work on something, or if we transfer heat to something, what do we do to that something? We change it. And so consequently, the two definitions line up. So yes, energy is the ability to do work or transfer heat, but working and transferring heat causes that substance to change, and so the definitions line up together. You okay with the idea? Okay, so guys, with that said then, we now need to talk about the 2 types of energy. I'm thinking that even if you haven't taken physics, you have probably encountered these ideas, and you certainly read them in the chapter. So guys, the first type of energy that I'd like for us to think through is kinetic energy. Did you know that was one of the 2? What's the other one? We'll talk in a minute. Okay, good. Okay, so guys, kinetic energy is the energy of motion. And I know if you've taken physics, this is starting to feel like physics. Guys, let me just look over the horizon and tell you about your futures. You ready, guys? By your junior year in college, your physics classes, your chemistry classes, your biology classes, and your calculus classes will all be doing the same things. It's horrible. I didn't take that much biology, so I never got there. But if I'd gone far enough in biochemistry, it would have happened. But by my junior year, it's differential equations. My DiffEq class, my physics class, and my chemistry class were all doing the same stuff, slightly differently. And so it's not a matter just of learning the material. You got to figure out how your chemistry, your physics, and your math teacher want it represented. It's horrible. So is this physics? Yes. But is it chemistry? Yes. So, guys, when we talk about kinetic energy, it's the energy of motion. This is the equation. Kinetic energy is equal to 1/2 the mass of a substance times its velocity squared. So if we want to give an object more kinetic energy, we can either speed it up or we can fatten it up. Because, guys, kinetic energy is equal to 1/2 the mass of a substance times its velocity squared. This explains how it is that a skinny little free safety can tackle a big old running back. Because he's going faster. The running back's got greater mass, but as a result, they're probably slower. And as a result, this little 170-pound free safety can run over the running back because they're moving so much faster. So guys, when we talk about kinetic energy, we're talking about this bringing together not just of mass, but velocity. But you'll notice that velocity is squared. Consequently, you get more bang for your buck if you can speed something up rather than making it heavier. Okay, so kinetic energy. Are we good? Good on kinetic energy. Okay, so now guys, we're ready to talk about potential energy. So guys, maybe we should do this quickly just so we're clear. In physics, it's kinetic energy all over the place. It's throwing balls. It's those little air carts on the run. Those are cool. It's just physics is all about kinetic energy. Guys, frankly, there's only one place where we're going to talk about kinetic energy in this class. Temperature. Right? Because when molecules move, when they vibrate based upon their kinetic energy, their temperature. So temperature is actually an indirect measure of kinetic energy. If you cool something down, it wiggles slower. What just went down? Its velocity, so its kinetic energy goes down. If you heat it up, it wiggles faster. Its velocity goes up and its kinetic energy goes up. So guys, in this class, we are going to limit our kinetic energy conversation to temperature, but we got to talk about potential energy a ton. So guys, let's define it. What is potential energy? It's stored energy. But guys, here's the trick. And we're gonna wrestle with this. How on stinking earth do you store energy? Okay, so hold on. Rather than a ball, allow me, if you would, just a second. So rather than a ball, let's go with a block. So what do we need to do to store energy in this block? Lift it up. This has got more energy stored in it here than it does down here. But now let's keep going. Because that's not the only way to store energy. Where else in your worlds is energy stored? In batteries. Okay, so we've got energy that, I do. So guys, we've got energy that is stored in batteries. Where else? I have one. We've got energy that is stored if we extend a spring. Where else? In wood. Yeah, good. So if we burn wood, energy stored in wood. On a related note, food. Oh, also in starburst. We'll figure out ownership later. Guys, where else? Okay, so there's energy stored in radioactive processes like uranium and other things. Where else do we have energy stored? Guys, this one's really important to me right now because my son just turned 16 and got a car. Gasoline. Okay, so guys, let's call that our exhaustive list. So we understand, no, guys, don't get distracted. Matt, focus. So guys, this is important you understand this. We can store energy in food. We can store energy in the nuclei of atoms. We can store energy based upon position. We can store energy in springs. We can store energy here. We can store energy in wood. All of these things represent ways of storing energy. What do they all have in common? Because guys, each and every one of these ways of storing energy stores energy in exactly the same way.
Well, I guess for like the block, it's based on the fact that it's gravity.
Okay.
Or in the battery.
Okay.
That the positive. The negative
Keep going. Keep good. Okay.
Or they just, it's all based on like a force.
Good. And what kind of force?
Conservative.
Not a conservative force. Do you want to add to this? Because he's on the right track. So don't take us in a new direction. What kind of force? Because it has to be an attractive force. So guys, let's talk about the attractive forces. What is the attractive force that causes this to fall? Gravity. What is the attractive force that causes the negative electrons to flow from negative to positive? It's called an electrostatic force, but you understand that negatives and positives attract. Guys, what is the force that holds this together? Strong nuclear force, also an attractive force. But what about this? What about food and wood and gasoline? What are the forces in there that we can leverage to store energy? Bonds. But do you understand that that's the same as this? How do bonds form? Ionic bonds? Positive and negative ions. What about covalent bonds? The positive nuclei being attracted to the shared electrons. Covalent bonds. So guys, you gotta understand this. All potential energy, whether it's gravitational, whether it's electrochemical, whether it's nuclear, whether it's mechanical, all potential energy is stored through attraction based upon position. So guys, potential energy is defined as the energy of position. And guys, when we talk about the energy of a position, it is always position relative to attraction. It's not just enough to have the attractive force. Because guys, if we take this block and set it on the floor, it no longer has any potential energy. And I know that you're writing, so we'll talk more in a minute. I'm going to ignore you for a minute, Matt. So guys, it's critical that you understand this. It's got to be both concepts in your brain. We understand, I hope now, that in order to store energy, we've got to have attraction. But guys, it's not just attraction, it's also got to be position. So why does this block not have any potential energy anymore? Can't fall. It can't fall. It has reached a position of zero energy, and now you're thinking to yourself, why do we need to know this? And the answer is because electrons do the same thing when they fall into the nucleus. Well, they fall down through the energy levels. We'll talk about the Bohr model next unit. But guys, the idea here is that there's always a position of lowest energy, regardless of what we've got here. That's why batteries die. There's always a position of lowest energy, and then relative to that attraction, if we can move that object out of that position of lowest energy, now we can store energy in it. Does that make sense? But you ready for a crazy connection? Guys, what do I have to do to this block in order to get it out of its lowest energy position? I have to lift it. And guess what the technical name for that is? Work. And we'll talk more in a minute. Okay? So guys, a lot of related ideas in your heads right now, right? So let's sort this out. Here's what we know right now. We talked about kinetic energy. Just put that away. We're done with kinetic energy for this unit. We're going to talk about potential energy. And guys, when we talk about potential energy, you all knew that potential energy was stored energy. But even if you've taken physics, I would doubt that you understood that we store energy based upon position, but that position is always relative to attraction. Did those two things make sense? Okay. So, may I continue to ignore you? Okay. So, guys, with that said then, we're going to talk very briefly about two types of potential energy. So guys, the first one, and please don't write this down. Bless you. There was two. You good? You okay? Bless you. Hey, so guys, don't write this one down because forgive me for saying that this is physics. We are not going to talk, don't write it down. We are not going to talk about gravitational potential energy in this class, but it was the first answer you gave me when I said, how do we think about potential energy? You said a block and lift it up. So it's really our frame of reference. So guys, let's make sure we're clear on this. Gravitational potential energy depends on mass, position, and gravity, right? The heavier something is, the more potential energy it's got. That's why you would rather drop the wooden block on your toe rather than the brass block, right? But then it's also a question of position. You would rather drop the brass block from here than up here, right? But it's also gravity. You would rather drop this on your toe on the moon because gravity is less. So it's a function of all three of those things. And so guys, let's take those ideas and now you need to start writing this down because this is the big one for us in chemistry. Electrostatic potential energy. Guys, this is batteries. This is bonding. This is chemistry stuff. This is important. So when we talk about electrostatic potential energy, we're talking about the attraction between charged particles. So let's talk about our potentials here. So if those charged particles are ions, or I'm sorry, protons and electrons, that's covalent bonding. Brandon mentioned this idea of covalent bonding being shared pairs of electrons. And if you've got a shared pair of electrons, that's negative. The nuclei are still positive. The nuclei are attracted to those shared pairs. That electrostatic force creates a covalent bond, and energy can be stored in those covalent bonds. If those things are ions, sodium ion, chloride ion, then we've got ionic bonding. But guys, we've also got the electrostatic attraction between polar molecules. And we'll talk more about that when we get into our unit on intermolecular forces. So guys, this is a good place to call time out. I know that this is going to start to feel like a lot of information, so let's sort of check as we go. So here's what we know right now. We understand that there are two types of energy that we need to keep track of. First of all, we understand energy is the ability to change something. How do we change something? We either do work on it, or we heat it up, or cool it down. So it's heat or work. Then guys, we understand that there are two types of energy. Kinetic, which is the energy of motion. We understand we're going to table that for now. And then guys, we also understand that there's potential energy, which is stored energy. And we've got this interesting idea now that energy is stored relative to attraction and position. And in chemistry, when we talk about attraction and position, we're talking about the attraction between negatives and positives, which is electrostatic attraction, and that plays out in many different ways. Questions? Go ahead. Oh, yeah. Mm-hmm. Yeah. 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 So why do positives and negatives attract? Why does the, oops, these are pretty weak, but I don't like my stronger ones. Why do the north and south poles of magnets attract? And the answer is we don't know. Guys, some of the most fundamental things about our universe. Why do magnets attract? We all understand that North Pole, South Pole, they attract one another. But guys, why? There's no physical attraction. There's no, let me say that differently. There's no physical connection between the North Pole of one magnet and the South Pole of the other. There doesn't have to be. There's nothing between them. And why do they attract? Why does a positive ion attract a negative ion in something like salt? There's no, and I know that we represent this with these little sticks as if there's something physically there, but there isn't. It's really a negative and a positive ion in close enough proximity, they attract each other and they make very stable structures that we call salts. But guys, why? Why does positive and negative attract? Why do masses attract each other? Why does the mass of the earth attract the mass of this and it falls when we let go? We call it gravity. Guys, why does that happen? And the answer is fundamentally, we don't know. Einstein's gotten close, the theories of relativity, at least to explain gravity. But why do positives and negatives attract? Fundamentally, guys, we don't have a good answer. Isn't that weird? If you were to ask, why gravity? Why is there a gravitational force? Why do things with mass come together? Fundamentally, we've got some ideas, but we haven't pulled it together yet. Isn't that weird? So here's what we've got to do. Whether we understand that gravity happens or not, whether we understand why magnets stick together, we know that they do. And so consequently, we've got to move forward with that understanding. If these are questions that are fascinating to you, get a degree in physics. And you'll get well along in these things, and you'll find that when I say we don't know, that's not completely the case. We're really closing in on ideas that we think are correct. So we're not completely shooting in the dark. If you've heard about the fabric of space-time and things like that, but they're not easy answers. So we're going to treat it because we know it works, but we're not going to explain it. Is that fair? Okay. So how are we doing, team? You okay on these ideas? All right. So guys, with that said, now let's start to quantify things. So units of energy. And of course, we're going to use metric units of energy. And so guys, when we quantify energy, the first one that you need to know is the joule. So guys, the joule is the amount of energy a 2 kilogram mass possesses when it's traveling at 1 meter per second. That is the definition of a joule. So once again, and it's not like you need to know that, but it may be, well, actually that's not true. You're going to find we do need to know this in the next unit when we start studying the energy of electrons, because in order for the units to cancel, you need to know this other definition of the joule. Go ahead. Good question. So why is it 2 kilograms? And guys, the answer, you can write this down with me if you want. So guys, that's the equation for the kinetic energy. And so if we plug in the values, this is 1/2 times 2 kilograms times 1 meter per second squared. And when we do that math, what does it work out to? 1. Because 2 divided by 2 is 1. 1 squared is also 1. So guys, the other units for joules is actually kilogram meter squared per, that's not velocity, that's seconds. The other units that we will use for joules, you may want to write this down. The other units that we'll use for joules is kilograms meter squared per second squared. but we just call them joules. Now guys, the problem is this. Joules are not a lot of energy. So let me help you visualize a joule of energy. So what in your world has a mass of 2 kilograms? 2-liter bottle of soda. What is the mass of a liter of water? A kilogram. So if you've got 2 liters of water, that would be 2 kilograms, forgetting about the sugar that's dissolved in there that makes it heavier. But guys, if you can imagine a 2-liter bottle of soda, which weighs about 2 kilograms, and if that's moving at about 1 meter per second, and if that were to run into a wall and stop, it just transferred 1 joule of energy into the wall. It's actually not much energy. Consequently, what we tend to use is we use kilojoules. Kilojoules tend to be our units of energy because joules are so small. Now guys, here's the thing that's interesting. In the United States, we don't use joules or kilojoules. What units do we use for energy? Calories, because think about it, we get our energy from food and food from calories. But guys, the reason that I have this bag of M&Ms is because these are from France. And it actually says right on the front of it, 1 bag is 45 grams and it contains 965 kilojoules of energy.
That's so cool.
Yeah, see guys, in France, they don't mess around with this calorie stuff. They measure their energy in kilojoules. Or, I guess, yeah, so it would be... You understand. You understand. But guys, we should at least relate this. We should at least relate this to what we know. So let's talk about the calorie. The calorie, by definition, is the amount of energy needed to raise 1 gram of water's temperature 1 degree Celsius. Guys, that is definitely worth writing down because it's going to become wildly important to you when we go to lab and start measuring the amounts of energy that reactions give off. The way that you'll find out we do that in lab is we run reactions in water, and then we measure the temperature that the water changes and use that to figure out the amount of energy that the reaction either released or gained. So this is an important definition. The calorie is the amount of energy needed to raise 1 gram of water's temperature 1 degree Celsius. But what does that mean in joules? Well, guys, the relationship is this. 1 calorie is 4.184 joules. And guys, that is exact. That is not 4 significant digits. That is infinite significant digits. So guys, let's talk about this then in general terms. Approximately how big is a calorie? Or I'm sorry, in joules, let me say it differently. Approximately how big is a joule relative to a calorie? About 1/4, right? If it's 4 joules in a calorie, then a joule is 1/4 of a calorie. Does that make sense? Okay, and you may even want to just jot that into your notes just as like a little mental conversion factor. It's about a joule is 1/4 of a calorie. But here's the problem. This is not the calorie that's on your Snickers bar. Guys, the calorie that is on your Snickers bar is not a lower C calorie. The calorie that is on your Snickers bar is a dietary calorie. And that is not the same as this. A dietary calorie is actually a kilocalorie, and it's written big C. So guys, when you eat a Tic Tac and that itty bitty little mint candy is a 1 calorie Tic Tac, that is actually 2,000 calories relative to our definition, which is the amount of energy needed to raise 1 gram of water's temperature 1 degree Celsius. So if you are on a 2,000 calorie a day diet, which may not be inappropriate given your guys' age and size, guys, if you're on a 2,000 calorie a day diet, that's 2 million calories relative to our definition of 1 degree Celsius. Get the idea? Okay. Okay, so guys, in my mind, here's where we are. We get kinetic, but we're going to move it to the side. We get potential. And now, guys, we have this idea of our units of energy, which are joules and calories. But we're going to use joules and kilojoules. You guys good? All right. So now, guys, we're done with the foundational stuff, and it's time to start setting the stage, if you will, for the way we're going to talk about thermochemistry for the rest of the year. This is new. Regardless of whether you've done chem or physics, you've got to understand this stuff. So guys, make sure you write these things down. This is going to become important, very important later. So guys, when we talk about energy and reactions, it is very important that we have a consistent frame of reference. Now here's the problem. Don't get too caught up in this. I think if I didn't say anything, most of you wouldn't even notice the difference, but I've got to say this because at least a couple of you are sharp enough that you'll pick up on this. Guys, in physics, you learned to study processes through a frame of reference. The best example would be the Doppler effect. Did you learn about that in physics? You understand the idea that if you're standing by I think they typically talk about a train. If you're standing by a train track, and as that train comes by, or as a car goes by on a road, you hear it go, "Eow," as it goes by, right? And the sound not only gets louder, but the pitch gets higher, and then the pitch gets lower. We're not going to talk about why, but it's called the Doppler effect. But if you were in the car, the pitch doesn't change. And the reason is because of frame of reference. If you're standing beside the road, as the car moves towards you, the sound waves are being compressed, shorter wavelength, higher pitch. As the car goes past you, the sound waves are now being stretched, longer wavelength, lower pitch. And that's why you hear that "eow" as it goes by. But guys, if you're in the car, it's just because you're moving with the car and the pitch doesn't change. Here's the problem, guys. In chemistry, you're always in the car. In physics, you're always standing by the side of the road. And this is critical. Guys, your frame of reference, and we're going to give these names in a minute, but guys, your frame of reference in chemistry will be the opposite of your frame of reference in physics. In physics, you are always an external observer. In chemistry, you're always in the middle of the action. Why do we care? It changes the signs. And this is going to be critical. So guys, whether or not you've been deep enough into a physics experience that you understand the difference, guys, this is critical you understand this. We use the term system and surrounding. So guys, the system is the portion of the universe that we are studying. The surroundings then are everything else. Now guys, here's the important thing you've got to keep track of. And I'm not going to say this again, but we'll say it one more time. If you've gone through a good physics experience, you probably know that your frame of reference is the surroundings. No more. Guys, in chemistry, your frame of reference is always in the system. So you may just want to do this. You, forever and ever in this class, are in the system. That is your frame of reference. So guys, with that said then, there's one other thing you need to understand about our systems. Actually, two other things. So guys, when we talk about systems, our systems will always be what we call closed systems. Are these things starting to sound familiar from having done the reading? Yeah, see how you're hanging knowledge on what you've already encountered? So you guys, in here, our systems will always be closed systems. And when we talk about closed, the question is closed to what? And the answer is this. In a closed system, energy can be exchanged, but matter cannot. Now, guys, I think some of you could probably already come up with this, but let's make the important connection. If matter cannot be exchanged in a closed system, closed systems then always support the law of conservation of mass. Does that make sense? Let that rattle around for a minute. What does the law of conservation of mass say? Matter never changes, right? Mass never goes up or down. So guys, if matter cannot get in or out of our closed system, which it cannot, then the law of conservation of mass is always maintained. So you may want to just jot a note to yourself here, reminding you that this all links back to the law of conservation of mass. Is that okay? So here's what we now know. When we study thermodynamic systems, we will always talk about the system and the surroundings. Here's the thing that's cool, guys. Who gets to pick the system? You. That's going to be one of the things that makes this study initially challenging, is figuring out what your system is. But the trick is the more limited you can make your system, the easier the math becomes. So guys, what's going to happen is you're going to pick the system. Once you've got the system, everything else is the surroundings, the rest of the universe, and you are always in the system. Now, our systems will always be closed systems, and that means closed to the exchange of what? Matter. You okay on that? But it does not mean closed to the exchange of energy. You get that? So now, guys, we've only got one more thing to talk about and we're done for the day. Are you ready to make this segue? So, guys, the question is this. How do we do that? How do we get energy in or out of a system? And, guys, the beautiful part is there's only two answers. There's only two ways to get energy in or out of a system. And it's not like we're dumbing this down because this is just AP chemistry, and when you get into college chemistry, they're going to tell you all the other ways. Guys, this is it. The universe that we live in, there's only two ways to get energy in and out of a system. Do you know what they are? Work and heat. That's it. That is the only way to get energy in and out of a system, is through doing work or exchanging heat. So guys, you may want to write down the subtitle here because it's important. Work and heat are the only ways to get energy in and out of a system. That's it. That's all you got. So, we call that amount of energy in a system, and you'll notice it's underlined, we call that amount of energy in a system the internal energy of the system. You know what, guys? I'm going to change this. I want to add something to this that I think will be beneficial just by the flow of the way this has come together. Okay, like that. Now let me figure out how to rework this. Okay, I like this better. Here we go. So guys, if you printed the notes, this is going to step out of it a little bit. Oh, wait. I don't like that, though. Okay, guys, here you go. I changed this a little bit. So, guys, the total energy of a system is termed the internal energy of a system. So let's make sure we're clear on this. If the total energy of a system is the internal energy of the system, how many different kinds of energy are there? I'm glad that you're hesitating because it would have been easy to say work and heat. Let's talk. Guys, the total energy of a system is termed the internal energy of a system. What are the two kinds of energy that exist? Potential and kinetic. That's it. Guys, the internal energy of a system is the sum of the kinetic and potential energy of the system. You okay on that? Two types of energy, kinetic and potential. And we've already defined those. Now, here's the interesting bit. Not only are there only two kinds of energy, there are also only two ways to change internal energy. And what are those? Work and heat. Work is abbreviated W, heat is abbreviated Q. Keep us on track. Are you going to keep us on track?
Yes.
Okay. You're not keeping us on track. We'll talk later. So guys, work is W, heat is Q. So here's where we're at. Ready? Closed systems. In a closed system, matter can't get out, but energy can. So what kind of energies are in there? Kinetic and potential. And once we know the kinetic and potential energy of a system, can we change the energy of the system? Yeah, how? Work and heat. That's it. Do you get the idea? Okay, now let's talk about what work and heat are. So guys, first of all, work. Work is defined as the energy used to cause an object to move against a force. At the risk of offending, are any of your parents like highway workers? No? They don't like pave roads or anything? Okay. So I can use the analogy and not offend. So guys, ready? Let's talk about work. We now at least have written down the idea that work is movement against a force. Okay? So guys, what are the two things that have got it? And this is critical as we move into Thursday. You got to understand this. What two things have got to be present for work to be done? Movement and something working against that movement. So guys, let me explain to you what I'm talking about. Imagine that you're a construction worker and you are digging a hole. So you're digging into this hole and you are moving dirt. Are you doing work? Well, let's check the characteristics. Are we moving something? The dirt. But is there something fighting against the movement of that dirt? Well, there's gravity that doesn't want to allow me to pick it up, but initially there's even the friction between the dirt clods that are keeping them locked in place that I've got to overcome in order to do work. Does that make sense? Okay, now, this is why I had to ask, you've all seen this, you've driven down the road, and you've got all these cones that force you to drive 11 lanes through one lane, and as you drive by, there's all these guys leaning on their shovels. And you are thinking to yourself, seriously, you held up all this traffic to jam us through one lane, and you guys aren't even working. Are they working if they're just leaning on their shovels? What's missing? Movement. If you're just leaning on your shovel, in a very realistic physics sense, you're not doing work because you're not creating movement against resistance. So we know that we can remove the movement. Can we also remove resistance? And this is harder. But guys, in theory, it can be done. So for example, if I take a block, well, let's take a lighter block. If I take a block, well, I'll do it up here so y'all can see. So if I take this block and if I slide it across the table, why does it stop? Well, let me ask you this. Did I do work to make it move? Yeah, right? So I did work and I'm pushing it. But guys, if I continue to push it, am I doing work? Yeah, right? Because as I do this, I'm doing work because I'm pushing against, what's the resistance? Friction, and it's all over. It's the friction between the table and the block, friction of the air pushing past this, and also inertia, which we're not going to talk about. But guys, let's just say that it's just friction is the only resistance. Could we, in theory, do this but not do work? What would we have to get rid of? The friction, the resistance. And guys, I bring that up because in a couple days, we're going to talk about how to set up chemical reactions so they can function without work. So let's drive this idea home. We're sort of priming the pump for next Monday. So we understand that I'm doing work, right? What two characteristics? I've got movement and I've got resistance. And so guys, we're saying that in theory, we could still be doing this and not doing work if we can get rid of the resistance, the friction. And we're going to talk about how to do that with chemical reactions in a couple days. But understand for now, that's work. Is that okay? Okay. So then guys, we need to talk about, well, here, let me give these to you. So force is any kind of push or pull. And you really don't need to know the equation for work other than to understand that it is force times distance. If you weren't applying the force, the resulting, the resisting force would win out and the movement would stop and work would no longer be done. And then guys, finally, let's just, and again, you don't need to know that equation. I think there might be one homework question where you're just calculating work. It's easy. And then guys, let's talk about heat. Heat is energy transferred from a hot to a cold substance. And guys, I don't know if you understand this. If you don't, you may want to underline this. Energy always goes from hot to cold. Heat always goes from hot to cold. Never the other way around. Why does energy always go from hot to cold? Go ahead. Yeah. Yeah, I like that. So cold has less energy than hot, and you'll always go from more to less. Yeah, absolutely. Okay. So guys, let's summarize verbally, and then we're going to play a little game. So here's where we started. We started today, and if you want to go back in your notes, you can. We started today by talking about energy. We said that energy is the ability to do work or transfer heat. That's what changes things. Then we made that connection. And then we went on to say there's two kinds of energy. There's kinetic energy, which is the energy of motion, and there's potential energy, which is stored energy. Then we went on to further dig into potential. Did I say that right? Potential energy is stored. Okay. Then we dug into potential energy, and we said two things have got to be true to store energy. What are the two things that we need to store energy, potential energy. What did they all have in common? Attraction and position, right? You've got to be in a favorable position relative to an attraction, and now we have the ability to store energy. Okay, so now we've got that idea. Then we moved on, and really quickly we talked about units, and we said joules and calories, and then we moved past that. And then we said, okay, we've got this thing, we did joules and calories, but then we also did system and surroundings. And we said the system is what? Part of the universe you're studying. The universe then is everything else. We call it the surroundings. So we've got the system we're studying, all the rest of the universe is the surroundings, and where are we? In the system. Good. Okay. And so now we've got this idea of kinetic and potential energy. We've got this idea of system and surroundings. We are always in the system. And then we just finished this conversation where we said our systems will be closed systems. And in a closed system, what can't get out? Matter. But can energy get out? Yes. How? Work or heat. And then we had this conversation about total internal energy. Total internal energy is the sum of the kinetic and potential energies, and those kinetic and potential energies can be changed either by work being done or heat being transferred to the system from the surroundings. You good? Okay. So guys, at this point, I'm going to stop recording. So for those of you that are watching the screencast, make sure you check the last slide, print the slides off the website, and get your homework.